For billions of years, a massive star exists in a state of hydrostatic equilibrium, a continuous tug-of-war between two immense forces. Inward gravity pulls all mass toward the core, while outward nuclear fusion pressure pushes against gravity. This fundamental balance was mathematically detailed by Sir Isaac Newton in his 1687's Law of Universal Gravitation, and later expanded in Arthur Eddington's landmark, 1926 book, The Internal Constitution of the Stars. To picture this balance, imagine a giant inflated hot air balloon. The hot gas inside pushes the balloon's skin outward, while the outside atmospheric pressure pushes inward. As long as the burner keeps firing, the balloon stays inflated. Similarly, a star remains stable as long as nuclear fusion converts hydrogen into helium at temperatures exceeding 15 million degrees Celsius. Another example is a heavy industrial pressure cooker. The boiling water inside creates steam that expands outward against the solid metal walls. If the heat source vanishes, the pressure drops instantly. In a star, nuclear fusion acts as that continuous heat source, holding up trillions of tons of plasma. When a star with a mass over 20 times our Sun burns through its hydrogen, it fuses heavier elements until it reaches iron. Iron is a nuclear dead end because fusing iron consumes energy rather than releasing it. When fusion stops, gravity wins instantly. This process was theoretically proven by Subrahmanyan Chandrasekhar in 1931 and later expanded by J. Robert Oppenheimer and Hartland Snyder in their famous 1939 paper on continued gravitational contraction. Think of a massive stone archway where every stone supports the central keystone. If that keystone instantly turns to dust, the entire stone arch collapses downward in a split second. The iron core in a star acts as that sudden void in structural support. Consider another example. A sealed glass sphere submerged 10,000 meters deep in the ocean. As long as internal pressure equals ocean pressure, it holds shape. But if the internal air is removed, the ocean pressure crushes it instantly. In less than 1 second, the star's core collapses from thousands of kilometers wide to a sphere less than 20 kilometers across, triggering a violent Type II supernova explosion. Once the core collapses past a critical limit, it forms an event horizon, the point of no return beyond which nothing, not even light, can escape. Carl Schwarzschild derived the exact mathematical size of this boundary in 1916 using Albert Einstein's 1915 theory of general relativity. To understand escape velocity, consider a rocket launching off Earth. The rocket must reach 11.2 kilometers per second to escape Earth's gravity. But if you compressed Earth down to the size of a small marble, its gravity would become so concentrated that the escape velocity would exceed 300,000 kilometers per second, the speed of light, turning Earth into a miniature black hole. Imagine paddling a canoe upstream toward a waterfall. Away from the drop, the current is slow and you paddle easily. As you get closer, the water speeds up. The event horizon is the exact line in the river where the current speed equals your maximum paddling speed. Once you cross it, no matter how hard you paddle, you are going over the edge. If an astronaut fell toward a stellar mass black hole, extreme physics would take over. According to Albert Einstein's 1915 field equations, time itself slows down near intense gravity, a phenomenon known as gravitational time dilation. Imagine two synchronized clocks, one worn by the falling astronaut and one on a distant spaceship. To the crew on the spaceship, the falling astronaut's clock appears to tick slower and slower as they approach the event horizon. To the astronaut, their own clock ticks normally, but they see the rest of the universe speeding up into fast forward. At the same time, the astronaut experiences Spaghettification, a term popularized by Stephen Hawking in his 1988 book, A Brief History of Time. Because gravity weakens with distance, the gravitational pull on the astronaut's feet is millions of times stronger than on their head. This intense difference stretches their body vertically into a thin strand of matter before they ever hit the center.